Hi everybody, this is Tom Cherry Holmes, and this is another video in the Retro Computing Archaeology series. Specifically, creating games for the Atari 2600 and 5200 using cross-development tools. But in order to do this, I'm going to have to set aside some context. Particularly, I'm going to show a tool that exists both in native and cross forms, show using that tool, and show the advantages and disadvantages of using native versus cross tools to accomplish the same task. So in this video, I'm going to use an assembler from a software consultancy called Sorcim. They made a whole bunch of different bits of software for a whole bunch of different microcomputers. But in our case, they created the assembler that Atari licensed as Atari Macro Assembler and sold as the ACT cross assembler. AMAC will be running on an Atari computer with Atari DOS, and the ACT65 cross assembler will be running on an S100 system running CPM. In each case, we'll be basically using this assembler to make some changes to some source code, assemble the result, and then convert that result into something that can be run on the development systems and or burned onto a cartridge ROM. So with that, let's go ahead and get started. First with the native solution. The native solution here will run a copy of Atari Macro Assembler, which is $199 retail as of 1983, on a machine with 48K of RAM, which retailed at $899. This was just the computer itself. A 6502 running at 1.79 megahertz, the custom chips, GTIA, Antic, Pokey, etc. But in each case here, one of the important things that we need in terms of software development is not only RAM, which we have 48K of RAM. We'll see that is barely just enough to take and assemble the dig dug that we're going to be assembling. But we also need storage to read the source code in and to write out the object code. On the Atari, the standard disk format is single-sided, single density. These disks are 90 kilobytes each. They hold 90 kilobytes each. I'm going to say that again. They hold 90 kilobytes each. So we need 4 of those to get 360 kilobytes worth of disk space. That is $1,600 just for the disk drives alone. If we take and figure in the disk drives, the cost of the computer, the printer, which is another $219 plus another $199, so close to $500 for the printer and an interface, another $150 for the EEPROM burner, we're looking at approximately $3,100 total just for the cost of the hardware alone. Add on an additional $200 for the macro assembler package so that we can do our software development. With that, let's go ahead and get started using this particular environment. In this case, we have a copy of Altera that is serving as our Atari. And we've set up 4 disk drives here on a virtual FujiNet device, which I'm using to take and house the 4 disks that we need for software development. The first disk contains a copy of AMAC and MLOAD and contain our object code. The next 3 disks are the source code that are split across all 3 disks, and all 3 disks are full with source code. When we get ready, after we've booted the first disk, we take and swap it into place so that everything is D1, D2, D3, and D4, so that everything matches up in the code and so that everything will assemble as expected. So now, first thing we need to do is to take a look and see what we have as far as a lay of the land here. We have 4 disk drives attached. On the first disk drive, we have a copy of AMAC and we have MLOAD and we have a copy of DOS so we can boot into our disk operating system. On drive 2, we have a copy of all of the first part of the source code. The main part of the source code is digdug.asm, and if we take a look at digdug by copying it out to the console or the E device, we will see that it is, in addition to the initial header here at the top, we've got some basic macros, but we basically have a file that is full of what are called include statements, which basically say to go grab the contents of this file over here and put it where the cursor is. And this file is just basically one big spine of those include statements for various parts of the program so that everything can be compartmentalized quite nicely and so that it can fit on the disk in a space-efficient manner. But the file we're really interested in is title.asm. And before we actually go in here, I'm actually going to take and copy the backup file into title.asm. And I did this because I did a rehearsal run of this earlier here, and I just need to put everything back the way I had it. So now, if we go ahead and run medit, which is the source code editor, medit is short for Mike's editor. So we go ahead, go to drive 2 and edit title.asm. It will give us a warning here indicating that we have limited free space to store not only a new copy of the file, but a backup copy of the file as well. Since I happen to know that we do have enough space, I can ignore the message and continue onward. So with that, we have the title here, and you can see this is a full screen editor. I can use the cursor keys to navigate through the file, and you'll see kind of unusually, tabs become these right arrow characters, and character turns become these down arrow characters. Now that I've moved down into the routine that I want to change, I actually want to change this blue color that's being set to GTIA color register, shadow color register number 1, and I want to change it from blue to green. We go ahead, make the change. I press the Option key to go into command mode, which as you can see, now there's a cursor down in the lower left-hand corner side, and I can type exit 1 to write the file and exit back to the disk operating system, pressing this Start key to confirm my command. So now we're back at the DOS menu here, and if we take a look at drive 2, we can see that we have not only the title.asm, but the title BAK backup file. So if we want to revert the change, we can. All we have to do is copy or rename over it. So with that, now we can actually use the assembler to assemble the results into a binary file. And here we have the front end for the Atari macro assembler, which asks us for a command line to pass to the assembler. Under CPM, this would be entered immediately after the ACT65, but in this case, since there's no command line, they provided a facility to do it here. So the next thing I need to do is I need to take and do a little swap-a-roo on my disks to make sure that the disks are in the right place. And with that, now I can reference the digdug source code that was in D2, now in D1, as D1 digdug ASM. And I want to make sure that the binary file is placed on drive 4. The parameter to specify the binary file is called H because historically this assembler outputs Intel hex format files. And even though this version outputs binary format files, the command switch hasn't changed. Normally, this is where we would also add things like specifying that we want to do a listing to the printer, for example. But because memory is so tight, I cannot do that safely. And so I have to just rely on taking the assembled and outputting an object file directly here. Any errors that happen as part of the assembly will therefore be logged to the console. Okay? And with that, we can now start the process. And so what is happening right here is that it is now taking those instructions, which you saw as I was paging through the title file, the individual instructions, LDA, STA, etc., and it is converting all of those into their individual numbered instructions and their parameters. That is machine language code format, and it is the format that the computer understands directly. And because this is a complex assembler where you can have labels to represent things like constants, represent things like variables, or represent things like places in a program to jump to, the assembler has to take and deal with the source code in 2 separate passes. In the first pass, it has to take and look at the source code as a whole and figure out where each and everything of importance in the file, that is a symbol, that is a label, an expression, a variable, whatever, and figure out and keep track of where that actually is, so that in the second pass of the assembly, it starts taking the individual instructions and their parameters and turning those into machine code. And anytime that it runs up against a symbol, it will take and look against all the symbols that it collected in pass 1 and insert those in as it's generating the output file. As a rule of thumb, especially on these older machines running at, 2 megahertz or so, it just so happens that for each kilobyte of binary that gets created, it takes approximately 1 minute of time to do so. And since we're generating a 16 kilobyte binary to go onto a 16 kilobyte ROM cartridge, that'll mean that this will take anywhere from 16 to 20 minutes to complete. So with that, I'm going to take and mute my mic and let the assembly process finish here. And when it finishes, I will come back. But because I'm not going to cut anything else out, I want you guys to experience the whole thing of having all of this assembled so you have an idea of really how long it actually took to assemble something real and substantial. See you in a minute. And there we go. With that, the end of the assembly. And we have 4 errors that we found here. And if we take a look at each one of them, we can see what the assembler did when it encountered them. Even though it encountered these errors, the assembler continued until it hit the end statement at the end of the whole assembly. So we still have a complete binary with just a few things that have been substituted. In the case of the first and the last errors, we came up against either a typo or a missing macro called LDR. And in this case, it took that to mean this is an invalid instruction. We will go ahead and replace it with 3 no-ops. No-op has the hex value of EA, so there are 3 no-ops in its place. For the 2 middle errors here, we have 2 symbols. The U errors, these are 2 unknown symbols that we don't know where they are. It didn't find them in the first pass, so therefore it couldn't resolve them in the second pass. And in each case, it put a 20 here because that's the hex opcode for a jump to subroutine, JSR, and it put zeros in its place. So JSR 0000 in both of those cases. We wound up with approximately 4 errors in total, with 1,561 labels. This is also the symbol count that the assembler encountered. And we have exactly 0100 hex bytes feet. That's 256 bytes of our 48K of memory free. After this has all been assembled, there is literally no room for anything else. And that should alone give you a good solid answer as to why it's a good idea to assemble on machines with larger chunks of transient memory available, such as on CPM machines. So with that, we can go ahead and come all the way back down here, and we can press the return key to return back to the disk operating system. Oops. Actually, let me cold reset here. I'll just cold reset here. Because I forgot to swap the disk, and so it kind of went, ooh, crap, I gotta go do something. So let's go ahead and boot in and see what we wound up with. We take a look and we will see, oh, wheel. Craptastic. That's an oops. Did it put it on D4? Okay, so where did it go? It deleted it. Oops, that little. Okay, I'm going to take and redo the process here, and I'll just pause until it finishes. And we'll come right back to this point. Okay, so now we're back again. What basically had happened was I didn't swap the disks, and the reset to go back into DOS basically caused the compiler to restart its assembly, which coincidentally erased the object file that we were just working on. So I had to do the assembly again. So here we are sometime later. We have dig-dug object. Now if we take and load it, recall that we had made one change to change the text from blue to green. And we can see that it has done so. Although it looks like there's a DLI that's resetting it back to blue here. There's definitely some uninitialized memory here, and this is undoubtedly basically caused by a couple of the compile errors that we had that came up here. So completely normal, but the change that we did came up and we were able to load it and test it using the Atari macro assembler. So with that, we're now done with this first part of the video here, and we can now go on to do the cross-assemble section. Now, the cross-assembled section here is actually going to be done on an S100 machine. And in fact, it's an MSI 8080, which was the first viable Altair clone created by IMS Associates in 1975. Announced in 1975, shipped in 1976. For roughly the same cost, assembled as an Altair here, with arguably better hardware, especially in the switches department. So the thing is that this computer by itself really doesn't do much. It only came with a small bit of memory, 1K, 2K of static RAM. And first thing you needed to do, you needed to add additional RAM. Well, in our case, you can have, since we have an 8-bit processor with a 16-bit address bus, we have a maximum of 64K of RAM that we can put in the address space. And doing 64K of RAM on a machine in 1981 would have set you back roughly about $1,000, which is ironic because if you would have waited into the first 6 months of 1982, that number would have been sliced in half at least due to the introduction of 64 kilobit DRAMs. So anyway, with that said, we also have, as part of this particular setup here, we have two 8-inch disk drives, which hold 256 kilobytes each, for a total of 512 kilobytes of viable storage. These drives are approximately $500 each, so we're looking at about $1,000 of estimated cost for these two 8-inch drives. We also need a disk controller, and then in our case, we have a Tarbell single density controller that retailed for about $399. Also a Centronic 739 printer, very similar to the Atari 825 for $399, okay? We have an SIO card, which is a serial input and output card that we need for the console, and that's $299. So we're looking at an out-of-pocket hardware cost of about $4,600, but we're already ahead because we have more memory, and we have a lot more memory, and we have a lot more disk storage, and we can add more disk storage much more readily. And if we need more than that, we can swap out the floppy controllers for hard drive controller cards to add hard drives. We can add double-sided, double-density disks for even more storage per floppy, etc. Now, the reason that we have these single-sided, single-density floppies is that these typically all have the same basic disk format, and that is IBM 3740 disk format. I've talked about this particular disk format before. If you don't know what this is, go and do a Wikipedia on it. It was part of an IBM key punch system, and because IBM threw their weight behind it, it became the prevailing standard for for so many 8-inch disk systems. So you can easily interchange data from one machine with 8-inch drives to another using this disk format. So it works out very well. We also need a VT100 terminal to be our console and to be our output screen as well, since the MSI only has the front panel with the lights and the switches here. So we get something that looks a bit like this, right? We have the MSI 8080 mainframe on top. We've got our disk drive cabinet down below with our two dual disk drives typically laid horizontally side by side there, going up to the disk controller in the cabinet. And if we can see to our right, we have, in this case, it's a Televideo 950 terminal, but the VT100 that we have here is very similar to this guy. So we basically have a terminal here providing the console functions for this machine. Off we go. And another thing that I will also state too, a big advantage to having something like this is the ability to have a card bus. And on many of these machines, you've got up to 18 slots of S100 cards that you can plug into a machine. One of those cards can be a ROM emulator. This is an example of a ROM emulator for an Apple II system called the Frob. And what we'll see right here is we have a card that has, as part of it, a couple of static RAMs right here and some logic to take and split that static RAM up into pages that can be shown in the expansion RAM's I/O area. And what this essentially translates into, you can see this long cable going out to what looks like a cartridge board. And that means that this card simulates a cartridge ROM. So you can take the end of this, plug it into a 2600, and plug this into your Apple II, load the software, and you will be able to develop games on the Apple II, assemble the results, and then send them right down the line to be played directly on the 2600. And you can see this additional board right next to it. That's an empty socket where you can place an EEPROM so that you can take your EEPROM, you can take your game, develop it, and when it's ready, burn it onto an EEPROM, put it onto this card here, and you have a prototype cartridge. So with that, let's go ahead and continue onward. Okay, we see right here. Cool. We've got some useful bits and pieces right here. If we actually take, we'll need to take, and looks like I need to clear my terminal display ever so slightly here. Let me see what you got here. Okay, that looks fine. All right. So we've got our terminal display over here on the left-hand side here, and I've got a front panel right here that I can take and manipulate with and mess with. I'll go ahead and turn the computer on. Now you can see the computer is on, our lights are on, and you can see a nice front panel display. This machine is ready to run. And so the only thing I need to do right now to boot our cross-development environment right now is to flip the run stop switch. And that puts us immediately into our CPM environment. Now at this point right here, we get a simple little sign-on message that informs us that we have a CPM 2.2 machine that is set up for 54 kilobytes of transient RAM. That means from the top of memory until we actually hit CPM, that is the BIOS, the CCP, the BDOS, and BIOS. That means we have 54K worth of viable RAM space that we can use to put whatever we need to in that RAM space. Part of that RAM space has to be taken up by the assembler, but the other part of that space is taken up by our source code. So we can load larger things in here. We already have more space to work with inside here than we did on our native Atari system here. It's sitting here waiting for us at a prompt here, which indicates that we are logged into Drive A and we can start to do commands. Well, unlike the Atari DOS, we need to send commands like dir to list the directory. And if we do so, we can kind of see what's going on here. We've got a directory of files on Drive A here. And Drive A is our system disk, and it contains all the utilities and things that we need in order to get things done. We've got, for example, WM which is WordMaster for our text editor. We have ACT65, which is our assembler. And we've got various miscellaneous utilities like MLOAD, which is our loader to convert hex format files into binary files. We have dump to do file dumps, etc., hex dumps, etc. All the bits and pieces that we need. And we have a pair of specialized programs, R and W, for getting the resulting artifacts off of our S100 machine and onto our host, onto our black box, so to speak. So with that, let's go ahead and get started. If we look on Drive B, we see our data directory, and we have right here a copy of the Atari 2600 Combat in source code form ready to go. And we've got some of the other bits and pieces that we're actually going to recreate as part of the assembly process to get this going. But first, we're going to take and do a little change to combat here into the play field. And we're going to use WordMaster, our editor, to do it. So we invoke WordMaster with the WM command with B: here and combat.asm. This loads combat.asm into memory and puts us into the visual editor. If you caught the edge of that copyright there, WordMaster is copyright 1978, and this was actually the antecedent to WordStar. We're going to use the key commands now to move down through the file, down to the end of the source code where the playfield definitions are to make our change. And you can see as we do it, we page through the various bits of source code. And since this is a full screen editor, and it's having to send the data across the terminal here, you can see it's actually painting the screen at 9600 bits per second. We'll take and hit the key a couple times here to get down close to the bottom. See how far we are here. Give it just a moment. We are right where we need to be. So we're getting close. And jet shape, these are hexadecimal values for the jet shape and whatnot. You can take these values, turn them into binary, and then plot them out on graph paper to see what they actually look like. And these are the jet shapes in each of their individual orientations, all pre-rotated. Because of the way that the Atari 2600 sprite hardware works, you only have to do enough of the rotations for a quarter turn, and then you can use the hardware to reflect on either axis. Almost there. This is controller tables that translate controller movements to velocity values, sound tables to translate sound tones to their register values, player widths, a color palette table, and finally, down here at the bottom, we see PF0_0, which are the values that go into the PF0 register for for this particular stage right here. So first stage, PF0 values. Let's go down, use Control X to come down here, and we'll scoot forward a little bit down over this line. And I'm going to change that from a 1-0 to a 3-0, which is going to shift the first little block over by 1, giving kind of an interesting border-like effect that we can see. Recall that when we actually did Stella here, in fact, I still have it running, you can see that the border currently looks like this right here. We'll take and put that over to the side. We make our little change, and then I hit the escape key and hit E to make our edit. At which point it saves the file and it saves the backup file. And you can already tell, even at this point here, the disk I/O access under CPM is considerably faster than it is on the native Atari system. First and foremost, bigger memory, faster disk I/O, more disk space so far. So now we do a directory on drive B, and we can see that we have combat ASM, but we also have a backup file ready to go as well. If we want to take and revert the changes, we can copy the backup file over the ASM file and revert our changes if we wish. But for now, let's go ahead and assemble. And to assemble, recall that on drive A, we have an ACT65 command. And the command options are exactly the same as they are on the Atari version of Macro Assembler. Same company, same assembler, same behavior. So we go ahead and say we want to assemble what's on drive B, combat.asm. And I want to take and go ahead and set the hex file for combat.x. Okay, and I also want to create a listing too. And I want to create a full cross-reference as well. These particular switches and their values are actually, even though we don't have the ACT65 manual, we do have the Atari macro assembler manual, and the options are the same. We go ahead, we press the return key. Now, since this is a 2 kilobyte cartridge, and we assemble at roughly the rate of 1 kilobyte per minute, this will take about 2 minutes or so to execute, even with the listing output. And we can see right here, you can see similar messages coming out of the ACT65 program that you saw in AMAC. It's the same program. They just ported it over. In fact, this program is actually a bit older. It's missing some of the commands that were added into AMAC, such as subtitle and a few others. And you'll notice right here, as it was doing that, if you were watching the front panel display down there on the bottom, you were noticing that the front panel was actually blinking as the computer was doing things. This was one of the nice things of having, about having a front panel available. Now, you'll notice that even with just, even with this here, we still had more memory available than we ever did on the Atari side. We had a lot more memory to work with, and we assembled a lot faster here. And what we wind up with are a couple of artifacts. Let's take a look at them. First things first, the file that we are actually after, we wound up with what's called a hex file. This is an ASCII representation of the machine language code right here, in a parsable format that can be sent over 7-bit lines, such as being sent over a teletype, to be punched onto paper tape, and other formats here too. It's ASCII safe, like base64 or UU encode. And as part of this information, it not only includes the data itself, but also information such as the address for where it needs to go, as well as a checksum and other things. That's the hex file right there. We still need to turn that into something we can use, but I'll also show you here that we also got, as part of the process here, a listing. And the listing contains virtually an output of every single line of the source file as it was interpreted by the assembler. In this case right here, we have a set of equates which take and assign labels to various registers inside the 2600 for the TIA and the Riot chips. And then finally, we get labels for each and every location in memory. Finally, we start seeing code. And we see with each line of code, we see the instruction on the right, we see any labels to the left of that instruction, but if we keep going left, we'll see the individual hex bytes, the individual machine language bytes that were translated for each one of those instructions and their parameters. SCI and CELD have no parameters, so they got assembled to single bytes. The LDX is a 0-page LDX, so we got a single byte. A2, which is the LDX, FF, and then so on. And it moves through the rest of the code. So you get to see what was assembled, how it was assembled, and where it was assembled to at its absolute place in memory. And you can print this out on a piece of paper. The whole idea here was to print this out on a piece of paper, to take and mark it up with your proposed changes, and then go back in with your text editor to make those changes, to do the next pass of the assembly, to iterate through the next phase of development. We'll go ahead and hit the Control-C here to get back to the prompt. And now we have an assembled file here, but it's not in binary format. So we need something to take and convert that into a binary format that our black box or /emulator, etc. can use. I'm going to use a particular program called MLOAD for that. Go back to drive A, we'll do MLOAD. MLOAD takes as its parameter its destination file. Combat bin, in this case, we want it to be a binary file. And the source material comes from b:combat hex. And it's going to take that Intel hex file, it's going to interpret it, figure out where it needs to load to, and then turn those hex bytes into binary bytes. This is normally used to turn an Intel hex file into a COM file to run under CPM. But since this is not a Z80 or 8080 piece of software, this isn't Z80 or 8080 code, this is 6502 code, all we really need the loader to do is to just convert this hex file into a binary file and be done with it. So we do this, it creates the file, and it gives us some statistics about the file here. So it's saying, okay, start address F000, ending address F7FF. There's no bias because we're not shifting it up by any number of bytes. And we say, okay, we've wound up with a file that's 2048 bytes long. That's exactly 2 kilobytes long to fill a 2 kilobyte EEPROM. 0800 hex bytes, 16 records worth. And we get a warning down here at the bottom that says the program origin, that is the first address of this file, doesn't start at 0100H. This is important for CPM programs because CPM programs must run at 0100H. No matter what you load in, CPM will always try to load a COM file at 0100H, and MLOAD is usually used to make COM files. But that's not what's happening here. We're making a bin file, so we can ignore this message entirely. And we have a bin file. We can dump it. And if we actually dump this file, this combat bin, we see the same set of hex bytes that we do in the listing, starting here at the top of this binary file. So we know we have something that actually corresponds to 6502 machine code. The SCI 7.8, the CLD D8, the A2, which is the LDX, the FF, which is the absolute value to put into the X register, followed by the TXS, the transfer of stack, etc. So we know we're on the right track. We see 20 F5BD to jump to subroutines, and we know, okay, we know this is sane, this is good, we don't have to go forward with it. We know this is okay. So now we need to get this to our development system. For that, we'll use the W command, which writes it to our development station. And this is an example of a bespoke command that is unique to your system and your environment to get what you've done off to where it needs to go. So W, and I'm going to do combat.bin. And it's going to take and write that out to my development system. So once that's actually done, I can then turn around and I can run Stella. We will run Stella with our new combat bin, and we can see our brand new result here. So if I take and turn on my development TV, you can see now that we've added in a nice little nib to the edges of each of the borders here. Because of the way that the combat kernel works, not only the left and the right are reflected, playfield are reflected, but the top and the bottoms of the playfield are also reflected in the same way. So that one change was reflected in all 4 corners of the playfield. So there we go. We have just taken and assembled, done a change to a 2600 game and pushed it out from a cross-development system and dumped it into our dumped it into our black box to play on actual hardware. If our black box was complex enough, we would actually have ways to be able to stop the hardware, to step into code to set breakpoints whenever certain things happen so that we could debug certain problems and so on. So with that, let's actually go ahead and move on. Let's say that some time has actually passed, and we are now tasked with doing 5200 type work. And we need to actually get used to doing work on the 5200. And as part of that process, we still use the same assembler, but we now get a new disk with some equates on it, just like with the equates that we have to map to registers on the 2600, we have equates to map labels to registers on the 5200. So let's go ahead and put this disk in. I need to stop my emulation ever so slightly here. Goodbye. And we need to do a little bit of 5200 dev disks drive B. Put that in drive B there. We will restart my environment here. And yeah, this little front panel emulation really is something awesome here, because you can see not only the front of the machine here with a faux reflection, but you can see the back of the machine here, how we have it set up. We actually have 3 separate ports set up here, one for the console, one for the keyboard, and another one that can be used, for example, for a modem. So let's go ahead and push that back here. Go ahead and do that, sure. And let's turn the machine on. Then let's immediately take and do what we did before. Just immediately start the run. And we're back in CPM as before. And now if we actually take and do on drive B, we can kind of see here a little README file, a little equates file, foot hex file, that sort of thing. And we can start to look through it. And if we do a little type here, we can see a little note that was left by the engineer, letting us know, okay, we've got an equate file with some registers for the 5200. System-wise, it's exactly the same as the 400, but the chips are in different locations, etc. Just a little note that they left for us. Okay, thanks, Bob. No, Bob is not a real person. Okay. So if we take a look a bit further, we can start to see more going on here. We can see equates for various system registers, for shadow registers, for interrupt vectors, and finally the different hardware registers for things like the GTIA, the ANTIC, the PIA, etc. All ready here and ready to be used. So what can we do with that? Well, let's see if we can at least do a basic little piece of software here that we know we can do kind of a smoke test. Well, to do that, I'm going to go into WordMaster here as I did before. And we're going to start with a simple little program that just takes and displays a rainbow on the screen as quickly as possible with as little code as possible. We'll go ahead and call it Rainbow. And we start off here in the visual editor here. But let's say I had something that I was going to transfer in over modem. I wanted to take and dump it directly into the editor and not have it waste time as I dumped it into the editor. Well, WordMaster has the ability to escape out into ED mode. And I can use ED commands to take and do what I need to, so I'm not burdened with the overhead of having to do full screen updates all the time. I'll use the insert command. The cursor sits right there and it's waiting for me to insert my code. We'll start with the rainbow example here. Get my modem ready. And with a little bit of finagling here, You can see the front panel lights are really going everywhere to take and build this. And actually, I'm going to do this a little bit differently here. Let me pause for just a second and pull this out and not try to do this from inside of here. I think I have a better way to do this. Hold on. Yes, indeed. That worked a bit better. Okay, so there we go. So now we've got this source code entered in. I take and hit the escape key, and we can go back into visual here, and you can see what actually got input. And if we scroll up, we can kind of see this very simple little program that just goes through and sets a couple of registers and does some WSync magic here to take and change each color of a line for each scan line on the background color register, as well as a few bits of data here at BFE8 or at the end of the cartridge to set a cartridge title and to set the cartridge year, as well as the start vector here, which is required by the operating system. So we've got that. Okay, great. Looks good to me. Let's edit and see what we got. So B:, we can see that we now have Rainbow ASM. How do we assemble it? In exactly the same way. Because of where the org statements are, we're starting at 4000, and we have orgs that go up to BFE8 and BFFE. This actually, and we're writing a word at the end of the statement here. This equates out to exactly a 32,768 byte cartridge. So let's go ahead and ACT65. We will take and do Rainbow. And we'll see that this assembled out very quickly. And if we do the MLOAD, do the same thing. Oops, sorry. Typed it wrong. It's important that you put drive B in both cases, because it was looking for it on drive A. Really? Let me look at something here. Did I accidentally make a humongous file on here that was much too big? Hold on a second while I see what's going on here. Ah, I see. That, wow. So the football game was much too large along with the corresponding hex file. I need to get rid of those files so I can have room for my binary here. No problem, we can do that. So, go. Here we go. Still going. So I will take an ERA foot, get rid of those files, and then we'll recreate. We can see that we've created the file. It creates a 32 kilobyte file here. And if we take and do a dump on this, we can see that it's our program right here with a lot of empty space in between, but it's here nonetheless. Looks good to me. And we can actually see that it actually created as part of the assembly process the hex file for our little demonstration program. Using the same tools as we did before, I'll take and bounce it over to my brown box, black box, brown box, etc. We'll write it out. The file has been written out, and I will now take and load it into Altera so we can use it. Take and attach the cartridge, and I'll go ahead, since we still have DigDug running over here, I'll just kind of keep it running here. So I'll say 5200, ready to go. And there's our rainbow test cart here. Looks like I need to change the naming of those bytes, but there we go. There's our rainbow, ready to go. It seems to be working. So our smoke test is doing great. Let's see if we can do something a bit, something a bit more. We can. All right. So let's take that, and I will just gently take and push you to the side here for a minute. And we will go back to my CRT. And we will now make a second file here to do some player missile graphics. As I read through what's been reverse engineered on the hardware, oh, we've got sprite registers, just like on the Atari. We've got 4 of them, just like on the Atari, and all the missiles can be combined together to make a 5th player, that sort of thing. Let's see if the knowledge that I have on my Atari work actually translates well over into the 5200. Write a little program. And since I don't want everybody to wait and get bored out of their skull waiting for me to type this all in, I will bring it over in just like I did the last time through the magic of paper tape here. So we go back into WordMaster here. PM test.asm. Sure. And escape, insert, and go. We've got some equates here that deal with the registers. These could just as easily have come from the PAM-EQU file, but they're up here at the top of the source code nonetheless. We initialize the computer in much the same way, clear out registers, then we start to set up the display memory the way we want it to, point all of the IRQ vectors to where we want them to our routines, and we start setting things up the way we want to. The display list, how the AMAC is set up, start drawing the graphics, and so on. We copy the player data to RAM when we start moving the player around. And finally, we wait for the vertical blank and continue onward. We want to do that so that we can keep the animation as smooth as humanly possible. Finally, we have the instructions for the display list and the graphic data for the player shape here too. We can see right here how the hex values correspond into their places on graph paper. Finally, just like with the other cartridge, we've got the area to have the game name, which we're not going to place in. And since we put an FF in the year value, it's going to skip over the initial splash screen and go directly into the game code. In Atari parlance, this is called a diagnostic card. So we go ahead, we exit and save our changes. There's our PM test right there, and we assemble it in much the same way. HB PM test, and we have a listing. Why not? And we'll go ahead and put a cross-reference at the end of that as well. And this is actually small enough, I'll actually show you the entire listing file here. So we go ahead, come through, read and assemble the file. It assembles in. We have plenty of RAM left over. And now, of course, just as before, we have a hex file that we can turn into a binary file. We have a listing. Recall before that you read the listing from right to left, basically. Comments, instructions, what those instructions assemble into, and what address they assemble to. Again, your listing is very important because that is your last line of defense to make sure that everything assembles how it's supposed to, where it's supposed to. Almost down at the bottom. Vertical blank interrupts, the display list interrupts, all the display list data, the reset vector, and finally, down here at the bottom, we start to see the cross-reference data. And you can see for the symbols, for each of the symbols, you see what those symbols resolve out to, and the first occurrence of it on what page, on what line, and the next occurrence on page, on page 1, line 10, page 2, line 57, and so on, going from left to right. So you can see how each individual symbol is actually used and where it is actually used. So again, like before, we just need to use the MLOAD command to turn pmtest bin, pmtest hex into pmtest bin. And like before, we wind up with a 32 kilobyte binary file. Again, the warning is here, it doesn't apply. So now at this point, all we really have to do is use our tool again. To bounce it out to the system. And we can then take and run it on our development system to see the result. Recall that when we left our black box for the Atari, for the 5200, it was running the Rainbow demo. So now if I take and tell it to boot the PM test, we can now see our demonstration here with players and missile graphics going in front of and behind playfield elements, showing how players and missiles and playfield priorities interact with each other. And you can see that these are changing as it bounces from one side of the screen to the other so that it appears to be going in front of and behind certain things. So with that, I think that pretty much covers all of the material. Let's see, make double sure that I have covered everything. And yeah, that looks like I've covered everything here. If you look at the description in the video, you'll find all my references to various bits of links to all sorts of things, such as the manuals for the various programs, links to the source code for things that I used inside this particular video talk, and other things as well. And one of the nice things here, you'll notice that the combat assembly didn't have any comments in it. And that was literally because I stripped them out so that it would fit in memory. If you want to read the definitive combat disassembly with all the comments, it's a wonderful read, and it's an excellent introduction into how to do Atari VCS coding. Conversely, the code, Dan Boris's page that I got this demonstration off of, is a great introduction into doing Atari 5200 coding as well. So with that, I'm going to go ahead and end this particular video here. I hope you guys enjoyed this. I hope this provided a really good insight into how applications, how programs, how games were developed on other systems so that they could be played on their target game consoles. And a bit of the workflow on how that was accomplished. If you would like to take and ask me more questions, or you want me to go into more detail in other videos for other things, please let me know in the comments. Let me know on Facebook. Let me know anywhere I post this, because I read everything everywhere. I will try to take and address it in the next video, because there will be more videos on this subject. There's a lot to cover here and a lot of knowledge that needs to be preserved. So until next time, guys, have fun.